Hello, everyone. I'm Eric Hyam, technical editor with Microwave Journal, and I'd like to welcome you to the next installment of our technical education webinar series. This webinar is entitled PolyStrata Delivers High Performance QFN Package Alternative. And the sponsors for today's webinar are RFMW and Nuvotronics. Today's presentation will be given to us by Tim Smith, product manager at Nuvotronics. This webinar will introduce PolyStrata, a groundbreaking technology that enables the creation of high-performance RF packages with form factors similar to traditional QFNs. By leveraging PolyStrata's unique properties, engineers can achieve superior electrical performance, including low loss, high isolation, and excellent signal integrity, while maintaining a compact package size. This presentation will explore the technology's underlying principles, design considerations, and real-world applications. Attendees will gain valuable insights into how PolyStrata can address the challenges of modern RF systems and unlock new possibilities for product development. But before we begin, let me cover a few logistics. If you'd like to download the presentation slides for reference, please contact Tim and the Nuvotronics team for that. We'll have time for questions after the presentation. To ask one, please type it into the Q&A window at any time. And the presentation is being recorded, so it'll be available to watch again and recommend to your colleagues. Now, let me introduce our speaker. Tim Smith is a packaging engineer with 14 years of experience developing innovative solutions for the RF and microwave industry. He's passionate about pushing the boundaries of packaging technology to tackle the toughest challenges in complex RF systems. He specializes in advanced packaging technologies, particularly PolyStrata, and has extensive experience in high-frequency microelectronic assembly and design. Tim has a proven track record of delivering high-performance RF systems that meet the stringent requirements of commercial and military applications. Today, Tim serves as the product manager for packages at Nuvotronics, where he continues to focus on leveraging PolyStrata to deliver innovative customer solutions. And with that, let me turn things over to Tim.
Hi, everyone. First off, a big thank you to our moderator for the intro and for setting this up. And thanks to all of you for being here today. I really appreciate it. Today, I'm excited to talk to you about how PolyStrata delivers high-performance QFN package alternatives. We'll dive into how PolyStrata technology is shaking things up in the world of QFN packages. I'll show you how it offers better performance with improved thermal and electrical properties, and how it tackles the issues we see with traditional QFN packages. Here's what we'll cover today. A quick overview of Nuvotronics, who we are, the industries we support, what sets us apart, and the types of products we offer. We'll go into a brief history lesson on electronics to highlight the importance of surface mount technologies. We'll cover the unique aspects of high frequency applications and why the use of low cost SMT processes has lagged in those applications. And finally, we'll discuss how PolyStrata offers a solution to this challenge. Please hold your questions till the end when we'll be opening the webinar to a Q&A session. We'll be happy to answer any of your questions then. Thanks again for joining us, and let's get started. First, I'd like to thank our co-sponsor for this webinar today, RFMW. RFMW is the premier specialty distributor for RF, microwave, and power management products. Their team of highly skilled, experienced technical sales professionals help customers find the best products for their design. To learn more, please visit their website at rfmw.com. So let's dive into what makes Nuvotronics a standout in the industry. As the inventor and producer of PolyStrata, we offer a unique and disruptive additive manufacturing solution that enables rapid adoption of millimeter wave solutions across various markets. First up, we pride ourselves on being an innovation powerhouse with a portfolio of over 100 patents. This innovation drives our ability to deliver exceptional RF performance, providing critical RF and millimeter wave solutions that disrupt markets ranging from 6 gigahertz to 100 gigahertz and above. Next, our design to manufacture footprint is comprehensive. We handle everything from design and fabrication to assembly and testing all under one roof here in Durham, North Carolina. This integrated approach ensures quality and efficiency at every step. We're also scaled for production with over 60,000 square feet of manufacturing space and 37,000 square feet of clean room space. Our production capabilities are available on both 8-inch and 14-inch panel lines, allowing us to meet diverse and demanding market needs. So let's dive into how PolyStrata technology is driving innovation across various markets. As you can see, PolyStrata is making a big impact in several key areas. In electronic warfare, our technology boosts advanced communication systems, giving them a tactical edge. In test and measurement, we provide precise and reliable components that are essential for developing cutting-edge electronics. In space defense, we support secure and robust communication links that are vital for defense operations beyond our atmosphere. In commercial space, our solutions facilitate satellite communications, connecting the world in ways we never thought possible. And finally, in infrastructure, millimeter wave technology plays a crucial role in urban development, enhancing connectivity within smart cities. All these advancements are driven by the need to move to higher frequencies in these applications, improve efficiency over traditional technologies, and reduce weight, size, and cost. There really is no other technology better suited to tackle these common challenges in high-frequency RF applications than PolyStrata. Today, we're reimagining the future of millimeter wave solutions with PolyStrata. Born out of a DARPA program in 2006, PolyStrata was built from the ground up to tackle the high costs and manufacturing challenges of millimeter wave RF systems. We started with smart material choices, using copper for conductivity and air as the dielectric. We chose micro-coax for signal transmission, ensuring micron level precision and repeatability, ensured a polished surface finish, all on a batch manufacturing process that can scale to meet demand. Every aspect of PolyStrata is focused on delivering compact, scalable, high-performance RF products. Our technology brings several key advantages to the table. It's ultra-low loss, ensuring minimal signal degradation. We have high thermal conductivity of bulk copper, resulting in efficient heat management for better performance. It's ultra broadband, supporting a wide range of frequencies from DC up to 300 gigahertz. We have a high level of integration, being able to combine multiple functions into a single compact solution. We have a repeatable performance from our photolithographic process and precision, which results in consistent results every time. We can manufacture at scale on our wafer and panel production lines, and the resulting products are smaller size and lightweight. And these features collectively address the common challenges in high-frequency RF applications, such as the need for higher frequency, improved efficiency, and reduced weight, size, and cost. Over the past 18 years, Nuvotronics has showcased the incredible solutions enabled by our unique manufacturing process. And as we transition to a product-focused company, we're excited to release products that allow our customers to also leverage these benefits, which brings me to my next slide. Nuvotronics has consistently delivered custom components that meet our customers' demanding specifications. As applications have increasingly moved to higher frequencies, we have successfully provided these advanced components to a growing market. Our products offer unmatched performance at competitive prices. We're also proud to introduce our low loss combining and splitting components, which are compatible with high power and available in both narrowband and wideband performance options. This expanding range of solutions empowers our customers to achieve their goals. Additionally, we've recently developed a new product family packages, which I'll discuss further in my presentation. Lastly, our integrated front ends showcase the unique capabilities of our technology, demonstrating what is possible with Nuvotronics' innovations. So today we'll be focusing on packaging. Before we dive into the challenges of RF electronics, let's take a quick look back at the history of electronics in general. Our journey starts in 1904 with John Fleming's invention of the vacuum tube. This device controlled electrical current in radios and other early electronics equipment and was actually an RF device. In 1925, we had another revolutionary breakthrough with the invention of what we would recognize today as the printed circuit board. In 1947, we saw the invention of the transistor by Bell Labs. This small device amplified electrical signal and paved the way for more compact and reliable electronics. Fast forward to 1958, when we saw another leap forward in technology with the integrated circuit. This miniaturized electric circuit design and was crucial for advancing computers and modern electronics. In 1971, we saw the introduction of microprocessors, single chip CPUs that became the brains of computers and countless other devices. In the 1980s, brought a pivotal shift with the rise of the surface mount technology and computer-aided design. SMT, or surface mount technology, dramatically improved manufacturing efficiency by allowing components to be mounted directly onto the surface of PCBs, reducing the size and increasing performance of the systems. In 1993, the introduction of the ball grid array packaging allowed for even more compact circuit board designs, which by eliminating the need for leads and wires on the package. Today, we continue to see a plethora of innovations focused on reducing the size and increasing the efficiency of electronic devices, even going down to 1 mil trace in space technologies such as blind vias, micro vias, flip chip, 2D stacking, 3D stacking. There is an unending list of advances that are currently going on today. Looking back, we can't overstate the impact that SMT had starting in the 80s on making electronics ubiquitous in our lives. This was the era when personal computing took off, with companies like IBM and Apple leveraging the economies of scale of SMT to bring down costs and make computers a part of everyday life. Before we move on, I want to highlight that when it comes to RF high-frequency electronics, we haven't advanced as rapidly as digital computing. For example, vacuum tubes, invented back in 1904, are still being used for high-power RF applications, although there is a growing trend towards IC-based solid-state solutions today. Still, a large portion of the RF market relies on chip and wire assembly methods, and are unable to utilize the key technology of the 80s of SMT that the rest of the electronic industry enjoys. So why is it that RF high frequency electronics still do not use SMT processes across the board? So to answer that question, let's take a closer look at the current state of high-frequency electronics manufacturing. On the left side, we see an example of current millimeter wave assemblies. These systems are designed for high performance, but come with challenges such as complex design, assembly difficulties, high material costs. Notably, there are no surface mount technology package devices available for frequencies much above 20 gigahertz due to the limitations in low-cost, repeatable manufacturing processes. Now, shifting to the right of the slide, we see one of those packages marketed for RF applications. These packages are adequate for some low-frequency applications, but performance dramatically drops off as frequencies increase. The illustration here shows how RF losses can occur in the wire bond transition from the IC to the package, and then again through the via down to the bottom of the package as it connects to the circuit board. These transitions can induce significant losses from parasitics that degrade the performance of the integrated circuit. These losses are critical because they may negate many of the benefits that SMT packaging solution offers, such as reduced size and increased performance. So in summary, while we've made significant advancements in the high frequency electronics manufacturing, RF losses within surface mount packages still keep high performance, high frequency systems from being able to utilize this low cost manufacturing process. Addressing these issues is essential to allow these systems to move towards PCB and SMT system designs. In this slide, I've collected some publications on 3 other technologies used for surface mount RF packages. These are all QFN style packages, air cavity, and you can see the general, this is insertion loss plotted by frequency, and the performance is above 0.5 dB up to 40 gigahertz. But really these, depending on the technology chosen, there's a dramatic drop off above 40, and depending on your application, even 0.5 dB insertion loss is not acceptable. So the dark blue line is plotting the PolyStrata QFN package performance, and you can see across the frequency band, even down below 20 gigahertz, our technology offers lower loss, and that loss improvement becomes even more dramatic as we move higher in frequency above 40 gigahertz. And this is because of our transmission line, a unique transmission line being coaxial, and the ability to tune the entire path with a lot of flexibility. How are we able to do this? We're able to do this by utilizing the PolyStrata technology I mentioned earlier, which is an additive manufacturing process which uses photolithography to define the geometry of a single layer. We electroplate copper on that layer, planarize to a precise thickness for that layer, and then we can repeat that process, putting another layer of photoresist down, patterning that, electroplating it, and going again. So typically our products are built, anywhere from 5 layers to 25 layers thick using this process. The XY dimensions are photolithography lithographically defined, so plus or minus 2 micron precision. The Z height is planarized to the same level of precision. And the surface finishes on the sidewalls, the bottom surface, the top surface of each layer are all better than 100 nanometers roughness. Here I've got a nice animation showing how one of our package products is built using this process. So you can see the first layer is deposited in copper, second layer. This is a key step that I'll pause, but the feed-throughs of the package, the dielectric that seals the package from the outside is a ceramic block, we call it, that that is placed, and the copper features are electroplated around that to form the seal and the transition from inside the package to outside. So the body of the package is solid copper with ceramic dielectric used only where it's absolutely necessary. And here you can see our our center conductor of our micro coax being formed along with the side walls, and then finally the top shield of that coax being formed there. After we build up the process, complete all the layers, the photoresist we use is sacrificial, so we go through a process called release that removes all that photoresist and leaves a pristine copper part. We then, for corrosion protection, passivate the copper in a immersion silver, immersion gold surface finish, which protects the part from corrosion, but also allows for wire bonding and for reliable soldering to the circuit board. The next steps would be die attach. Any internal capacitors within the package would be attached to the board, the package, excuse me. And traditional microelectronic assembly process can be used with this. We recommend the use of silver epoxy or silver sintering paste for high power die applications, die attach applications, and then traditional wire bonding processes can be used. The package substrate is pretty robust to aqueous washes, high temperature extrusions. Sorry, excuse me. It can easily survive solder reflow, die attach processes, wire bonding. Essentially, it is a copper and ceramic material set, so very, very robust material set for surviving many typical microelectronic processes. Finally, a lid is attached. We recommend a metal lid in applications where heat is intended to be removed from the top of the package. Alternatively, a plastic or ceramic lid can also be used. And epoxy or solder lid attach processes are compatible. Going to a little bit more detail on the design of our PolyStrata packages. Here you can see example of die attached and wire bonded to our transmission line. We generally advise a ground, 3 bond wires, ground signal and ground, to do these. And you can see how we are able to bring that transition in right up next to the edge of the die on the same height, therefore minimizing the wire bond length, minimizing your inductance, and minimizing the amount of parasitics that that result from that mismatch. We 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 take great pride in our 3D simulation that we are able to do on our package designs, and we fully simulate all these transitions to ensure that the performance is adequate and up to our expectations. So both the wire bond transition is optimized, the PCB transition is also optimized to ensure performance. And then this entire package can be easily surface mounted onto a circuit board. So the body of the package, as I've mentioned before, is built from solid copper. This enables maximum thermal spreading across the footprint of the device. Essentially, every location that is not a signal pin is part of ground and thermally connected to the backside of the die. And this allows us to spread the heat efficiently, and with the use of a copper lid, can a unique aspect of our QFN packages is that effective heat removal through the top of the packages is possible. Generally, the performance matches what it would be if a heat sink on the bottom side of the PCB was used. But in many cases, in PCB, SMT systems, the circuit board is very densely populated. Oftentimes, both sides of the circuit board are used for components, and so having the heat sink at the bottom of the PCB is sometimes not an option. So it's very advantageous to be able to remove the heat through the top of the package. Very similar to how CPUs and GPUs are cooled today in PCB in desktop computers and laptops. Like I said, we since 2006, 2007, we've been building systems and components for customers, typically defense, aerospace applications that have very demanding environmental requirements. And so as a technology, PolyStrata is shown to be robust, even through mechanical shock, high vibration loads, moisture, and humidity and temperature cycling all have passed some of the most rigorous tests for microelectronics. As a standalone package, we have tested our parts to MSL level 1 and pass. That is not to say we are hermetic, but that we don't our packages don't have any of the issues that a plastic package may have with popcorning or moisture absorption, and then going through a thermal reflow event. Our passivation, our finish, our immersion silver, immersion gold finish, we recognize is a rather unique on the market, but we have been using it for years for both solder PCB mount applications as well as wire bonding, and we've shown that through wire bondability tests and board reliability tests that this passivation is or finish is reliable in both applications, even after seeing multiple cure cycles or solder reflow cycles, it's still able to retain bondability at with high reliability. Hermeticity is often a question that gets asked, and I like to address. We have a path towards these parts being hermetic. The material set, ceramic and metal, are definitely capable of being a hermetic seal. We are working through the key interfaces between those materials to make sure they're reliable and can be marketed as a hermetic package. But today we do not claim that our packages are hermetic, but they do pass gross leak tests and effectively protect the die through the surface mount processes, cleans, etc. We have built a small set of our packages with the Qorvo CMD 247 die, bare die. It's a 20 to 40 gigahertz LNA, and we did run through a typical 8585 test for 168 hours. Ran it through reflow 3 times, and then retested and showed no change in performance. So passing well there too. Some examples of the benefits of our package are shown here. On the left side is a K-band LNA case study that we did with Northrop Grumman's ALP 302. This is a high gain, low noise figure device targeted to the K-band receive SATCOM receive applications, and in these applications, the noise figure of that LNA right after the antenna is critical to system performance, and so any increase in performance results in system level benefits. So while we're still tuning and optimizing this design, we have been able to show that we can, with Northrop's die, get down to below a 1.2 noise figure floor. There's a lot of that. Those measured results. There's a lot of jitter in there. I think that's comes from the measurement setup, but we're confident in seeing these results to show that we can achieve a very low loss transition from the circuit board to the active device. The other application benefit is thermal performance. So the RF performance is shown on the left, and the thermal performance is shown on the right. In this application, example, we show a 40 watt dissipated 40 watts of dissipated energy through the backside of the die for a power amplifier. And at the bottom there, you see the comparison between the different heat paths. So on the left side is absolutely not acceptable thermal rise of 340 degrees C. That case is when when you've applied a heat sink to the bottom of the circuit board, but you're unable to apply any kind of thermal vias or copper coin in the board because of routing or density of routing underneath the part. So you're depending on the thermal conductivity of the laminates to conduct heat down to the bottom of the heat sink, to the bottom of the circuit board to the heat sink, which these laminates are inherently very poor thermal conductors, especially in comparison to copper. So then on the right side, we show exactly the same setup, except we've now removed the heatsink from the bottom of the circuit board and put it on the top of our package. and you can see there's a dramatic improvement in the thermal resistance, which is resulting in only a 61-degree temperature rise from the backside of the die. So today we're excited to share that we have these QFN packages available, air cavity, with built with our PolyStrata technology. On the left-hand side, we have an example of the layout of the package that is available now, sampled through RFMW. They are, targeting amplifier products, two-port RF products that have an RF in, an RF out, and gate, gate and drain bias needs, and those are available today from package sizes starting from 3x3 millimeters up to 9x9 millimeters, and what that equates for in terms of die size is 1 millimeter by 1 millimeter die up to 5x5 millimeter die. It is possible to get even larger packages up to 20 millimeters by 20 millimeters, and for custom designs. We're also working on releasing another set of family of standard packages that have these RF pin connections on all sides of the package. So it provides a little bit more flexibility for multiple port RF designs, components, but maybe less pins altogether. So, and another thing I want to share is we are opening up our design of these packages. We are open to providing the building blocks. So the RF transition that's shown here on the left that works broadband up to 50 gigahertz, and the DC transitions we can in a very straightforward manner manipulate where these are placed on the perimeter of the package, how many of them there are, and the size of the package to optimize a design for a specific die. So shown here is the TGA 2962 device from Qorvo, and I'm showing how this is a custom design for that device. And you can see how that is similar to the standard products that we've shown on the previous slide, just adjusted to the needs of that amplifier. So that's something we'd like to discuss with our customers. Interest in custom solutions, which I'm sure there will be many. So going back to our standard product offering, these are packages that are available today. The top two are examples of custom designs we've done, but are open to anybody who is interested in building with them. They are custom designs for the ALP 302, the Northrop Grumman LNA we showed previously, as well as a 20 to 40 gigahertz power amplifier from Qorvo, the QPA 2640. The remaining 10 are our standard packages that I showed before that have a RF input and RF output and bias pins on the north and south side of the packages, and those are available in those 5 different sizes. So I'd like to thank you for attending this this webinar. That concludes my presentation, and we'll open this up for questions.
Thanks, Tim. That was an excellent presentation, lots of good information, and certainly some impressive results. Now, let's take a look at the audience questions, and please remember, it's not too late. You can still submit a question in the Q&A window. And let's get started with this one. Is flip chip possible?
Yeah, so our current offering is just for wire bond, but we have demonstrated flip chip interconnects to PolyStrata, and it is on our roadmap to support flip chip type connections into packages based on the technology.
Excellent. Thank you. The next question is, are the 3D design files available and what tools are supported?
Yeah, we have all the 3D design files for each of our standard packages available on our website, and we supply the 3D CAD in a step format. We also have on there the 2D CAD as well as the recommended circuit board footprint and the S parameters for the RF transitions, along with application notes. So all the support material that you would need to do the design is available through our website.
Great, thank you. Does this process require the inclusion of surface roughness in 3D EM simulations to achieve good correlation between simulated and measured performance?
It does not. The surface roughness of our material is highly polished. So the default of simulation software where it's assuming a perfectly smooth surface is actually pretty close to reality. Obviously when you get up to extremely high frequencies like 600 gigahertz, maybe that surface roughness will start to play in there, but generally no. Surface roughness is not a big factor on variation from simulation.
Good, thank you. Is the QFN package available for Nuvotronics filters?
So we offer these standard packages for designed for mimics. If the intent is to put a filter in the package instead, that's definitely possible. Yeah.
All right, thank you. What would be the lead time for a custom package design?
A custom package design from design start to receiving the product is typically going to be 16 weeks. A large portion of that is just taken up with the design and doing the design reviews with the customer, making sure validating it, and then so fabrication time is typically 9 weeks for these parts, and we have the option to expedite when needed.
Great, thank you. You touched on this question a little bit, but this is perhaps a bit of an offshoot. For your standard packages, what design data do you share with interested customers? Are CAD files or S parameter files available?
Yeah, so CAD files and S parameter files are all available for our standard packages online. And for customers who are interested, we can even discuss providing simulation quality CAD data, with material properties, etc. If that's something that a customer would want.
Excellent, thank you. Do you supply the lids for your packages?
So we don't provide lids today. The reason behind that is, we build parts using our technology, the PolyStrata technology, and the building the lids with our technology would not be very cost effective. There are lower cost ways to build simple parts like that. So we are working with third-party vendors to source lids. The standard packages are standard QFN sizes, so 3x3 millimeters, 5x5 millimeters, and so lids, plastic and ceramic lids can be sourced for those. We are working on sourcing metal lids, and for prototype purposes, we're more than happy to provide lids to customers. But in production, the intent is have third-party vendors supply those.
Good, thank you, Tim. How do the costs compare with other standard packaging solutions?
So we can be cost competitive with air cavity packaging, specifically ceramics, and because of our manufacturing process, in volumes we can be very, very competitive. Welcome any challenge to what costs need to be. Obviously there is a difference between costs for prototypes and low volume and high volume production. So just to give you an idea, our standard packages are available through RFMW, and those can be ordered today. Their pricing for small low quantities is going to be in the range of $15 to $50. That's I recognize that's more than what you might be able to buy a ceramic package for in lots of 1,000 or 10,000, but that's not those are for onesie twosies. So for production volume, I welcome the discussion on what pricing needs to be for your application.
Great, thank you. Can a ceramic leadless chip carrier be utilized in the PolyStrata package?
Yeah, I don't see why not.
All right, that was a simple answer.
Yeah, I haven't looked at that. We're typically just attaching die, but if you want to attach a die to a chip carrier and then have that bonded into the package, that's not an issue.
Good, thank you. There is a CTE mismatch between typical ICs and your copper packages. Isn't this a reliability concern?
Yeah, and maybe that's where that question about the leadless chip carrier comes from. Yes, our parts are our packages are bulk copper. They have the CTE, of bulk copper, the thermal expansion of bulk copper, and that's quite high compared to typical IC materials like silicon, germanium, and GaN, gas, indium phosphide. We recommend the use of bonding materials that are designed to join dissimilar CT materials. So there's silver epoxies, and for higher power applications, there's the silver sintered pastes, and they are designed to bond materials with differing CTEs, but maintain electrical conductivity, and in the case of silver sintered paste, high thermal conductivity. And these are both ways that we've been able to address that reliability concern. Alternatively, you can, similar to how you solve this problem in a traditional housing that may be copper for thermal conductivity, you can gold tin solder the chip to a chip carrier that is maybe copper moly, copper tungsten, and then bond that carrier into the package. And that's also a successful way to mitigate that. But yes, definitely CT mismatch needs to be considered when bonding the die into our packages.
Excellent, great, and that takes us to the end of our questions. So I'd like to close the webinar here. Let me thank Tim again for the presentation and for answering questions. Those were some thoughtful, thorough answers to those questions. And I'd also like to thank RFMW and Nuvotronics for sponsoring this webinar. As I mentioned, the webinar has been recorded and it'll be available to watch later today. You'll find it in the events section of the Microwave Journal website under the Archive Webinars and Events tab. So please feel free to watch it again or share it with any of your colleagues who may be interested. And remember, if you aren't already a subscriber to Microwave Journal, you can sign up on our website. The subscription is free to members of the industry. Now, let me close by saying thanks to everyone for joining us today. Keep an eye out for upcoming webinars and panel sessions, and I hope you all enjoy the rest of the day. Thank you.